Hello, everyone. I hope all of you are doing great and staying safe. On behalf of BioPetrol, Arab Oil and Gas Academy, and SPE Egypt section, I'd like to welcome you to our third interesting webinar about hydraulic fracturing. This course consists of 4 webinars, 4 quizzes, and the final exam. First, let me introduce myself. My name is Selma Rashidi. I'm a petroleum engineer. I owned my bachelor's degree from the American University of Ras Al Khaimah.
And my name is Shahad Bahjat. I'm a third-year petroleum engineering student at KNU in Kurdistan, Iraq, and we will be your moderators for today.
Our lecture today will be delivered by a very special guest from the University of Houston. Professor Mohamed Soliman is the chairman of the Petroleum Engineering Department. He holds 35 patents on hydraulic fracturing operations, analysis, testing, and conformance applications. He is the author or co-author of over 250 technical papers and articles in petroleum engineering. Professor Soliman is a registered professional engineer in the state of Texas. He is also a well-known member of the Society of Petroleum Engineers and the National Academy of Inventors. He has authored several book chapters on stimulation and testing. Also, Professor Soliman is the primary editor of Fracturing Horizontal Wells, published by McGraw-Hill in 2016. He is a co-author of Optimization of Hydraulic Fracture Stages and Sequences in Unconventional Formations, published by CRC in 2018. Professor Soliman holds a bachelor's degree with honors from Cairo University, master's and PhD from Stanford University, all in petroleum engineering. So basically, we will have an informative session by a knowledgeable person, so please make the most out of this lecture. Professor Soliman, the mic is yours.
Thank you very much. Welcome, everyone. I hope you enjoy the lecture. The lecture will talk a little bit about fracture design. We'll address several issues that we have in fracturing. I hope you enjoy it, and if you have questions at the end, we'll try to address a few questions, but you can always send other questions to me on my email, which will be mysoliman@uh.edu. If we run a fracturing treatment, this was basically a test which we ran very small fracturing treatment, but it shows what usually happens. In this specific case that we ran it many years ago, where we had downhole gauge, and we monitored the pressure rate, and we also monitored proppant if we have some. So you can see here, like what we talked yesterday, and I'm going to show another slide that even shows that even more clearly. As you inject the fluid, you can see if I have injection rate, I have downhole pressure. As I inject, the pressure will increase. At one point, I'll break down the formation. If you attended last week and we talked about it, there is a breakdown that if you remember, we looked at the equation. I asked you to maybe go through the derivation a little bit. It is 3 sigma h min minus sigma h max, and the fracture is perpendicular to minimum stress. And you can see it once you break down the wellbore, the formation, pressure will decline. Then it should stay constant or increase a little bit. We'll talk about that a little bit more in this lecture. And most models we see some increase in bottom hole pressure that has people use it in analysis. We'll discuss that. But that would be indication of fracture propagation. You can see I have a slurry rate here. There is not much of proppant concentration. This is mostly like a test. And you can see at one point I'm going to shut down, stop injection, pressure would decline. The sharp decline in pressure We'll see more exaggerated case in a minute. That will be an indication of near wellbore friction inside. But with downhole gauge, that's what I'm going to see, the near wellbore friction. If I'm having surface gauge, then I see sharper decline, which will indicate the friction inside the tubing or whatever inside the wellbore going from surface down to downhole. And once I will stop, there is some pressure decline. Next week we'll talk about analysis, very much analysis of this area here. What happens when you stop injection and pressure will decline. That will cover it in fracture testing. This is another case that we looked at, and you can see sometimes people either they monitor like this orange line, the tubing pressure. This will be surface pressure, or you monitor downhole pressure. So there is a lot of things that one will monitor during fracturing treatment, and it is not monitored for no reason. We are going to see, as we talk about today and the next week, a lot of this data need to be analyzed. People analyze it. Some of it is real time, some of it is after the fact. We'll see how we do that. Okay, this was a test, and was run many years ago. Actually, I was on that job. It's interesting. It's what we call microfrac. I'm going to discuss it more in detail, what microfrac is later on. But the reason I'm showing you this slide is to show a very controlled test. You can look here. I have injection rate showing here. I'm injecting, I'm shutting in, injecting, shutting, and so on. So I fractured this wellbore 3 times. The very first time, you can see pressure increased very much, and at one point, here we see very sharp drop in pressure. Actually, this point here, this sharp point, is where you broke down the formation. That is the breakdown. Once you break it down, this sharp resistance, the hoop stress we talked about last week, you can see here, once I overcome that hoop stress, pressure will decline very much. So there is a drop here. Some people have taken this value and say, well, if I know minimum stress, I can also calculate maximum horizontal stress from here. Sometimes it works. So here I'm injecting, so there is some propagation, and then at one point I'm shutting down. So you go from here to here, very sharp decline. Eventually, you lose pressure inside the fracture, and the fracture will close. And so one can use data here from the shut-in down to fracture closure, and from fracture closure down, you can do some other analysis. So that will be before the closure analysis. This is the after closure analysis. We'll discuss it a little bit next week. The fracture closure pressure is very important value. And the reason for that, if we're running a test and the amount of fluid that we're injecting is fairly small, that closure pressure will be very close to the minimum in situ stress. The far field stress we talked about last week. So what happens now if I come back and after some time, I start injecting again? Would I see that breakdown? Of course not, because you can break down the formation, and this is a vertical well. You can break it down only once. So when I start injecting again, at one point, I'm going to reopen that fracture again. So I'm reopening the fracture. Opening the fracture is a lot smaller than the reopening pressure, is a lot smaller, of course, than the breakdown pressure. Because here I'm just overcoming the minimum stress. In the breakdown pressure, I'm overcoming the hoop stress, which was the 3 sigma min minus sigma max. So here we did the same thing. So we repeated the test a couple of more times. And we wanted to see whether I have consistency in fracture closure pressure. Where we did, we had consistency of ice IP, that's near fraction pressure. And another issue I want you to, we're going to, it's going to affect what we do in testing, but you need to know a little bit about it, because this is a very famous equation that was developed many years ago. People call it Carter's equation, basically showing as you're injecting fluid inside the fracture, you expect a couple of things. You expect the fracture is is propagating, so there is some fluid staying inside the fracture, otherwise it would not be opening. So I have fracture volume, but I have some fluid that is leaking off. And that fluid that's leaking off, I'm going to call it leak off volume. In many of the experiments we do in the lab to determine how much fluid would leak off, would eventually it follows a shape like this curve. Basically, linear flow, there is some early fluid flow that will leak off very fast. I call that spurt loss. So that as soon as the version formation gets exposed to a high pressure fracturing fluid, I'm going to see fluid leaking off very quickly, more or less instantaneously. I call that a spurt loss, and then it follows a straight line that I'm plotting versus square root of time, and the slope of that straight line is my leak off coefficient. If you remember, in the first week we talked 2 weeks ago, we talked about linear flow being always shows itself as a square root of time. You may not remember that, but let us repeat it here. So usually when you have linear flow, it is linear function of a square root of time. If you remember when we talked about infinitely conductive fracture. So, however, in many of development of analysis, like in testing, since the spurt loss is small, they approximate the whole thing with a straight line going through zero. So there is some more extra work that one may do. We actually published some work in the area where, rather than assuming the spurt loss is too small, we actually considered a value to it. It's kind of interesting solution that, but we have developed the industry so many new solutions now where we, rather than using leak off coefficient, we depend on fracture permeability and say, well, this is dependent also on fracture permeability, and one can develop solutions for that. We'll talk about some of those solutions next week. With a fracture, I'm going to give you just a little bit of what is equation that people will use in simulating fracture and solving those equations. Basically, most people will assume that the pressure inside the fracture is constant. So there is not much of a pressure drop inside the fracture during propagation. So that's except near the tip. Near the tip of the fracture gets very narrow. And so many of the solutions we'll talk about today will have this assumption here, saying the width of the fracture is function of E prime. E prime, I defined it here, is the plane strain modulus, which would be equal to Young's modulus divided by 1 minus the square of Poisson's ratio. So if Poisson's ratio is 0.3, so square is 0.09, so it is Young's modulus divided by 0.91 if it's 0.3. One important parameter that people look at is stress intensity factor, which is nothing but the pressure inside the fracture times the square root of length, fraction length. And you usually this term, people look at it as psi per square root of inch, not foot. So you can see when the fracture is very, very short, just starting, this value may be fairly small. Once the fraction length gets a little long, this value gets really large. Why I'm talking about it? Because this value needs to be greater than KIC. KIC is the critical stress intensity factor, or you call it fracture toughness, which is function of the formation. So let us look at what values we have for formation for this KIC. It is sandstone is maybe 1200 to 1500. So you know if your pressure inside your fracture is of any significance, once it becomes a couple of feet, the fraction length is a couple of feet, it will be, the KIC doesn't come into play anymore. It's not that important. Which, when you think about it, if once you can see if you hold a piece of, say, wood, and it has a little crack, and you try to extend that crack, if it is very short, it is very difficult to extend it. Once it gets along, the pressure time length becomes so high that you can overcome the resistance, the fracture toughness of the formation. You can see here sandstone 1200 to 1500, shale maybe a little smaller. Granite is fairly high. One would say, why do you worry about granite? Actually, there is a lot of new work being done on granite, including here at University of Houston, but that is a research subject we can talk about some other time. One thing, when we talk about plane strain, many of your is 2D and pseudo 3 models will talk about plane strain. We're assuming that whatever happens, if I have fracture, whatever happens, all the strain remains in this plane. When I deal with pseudo 3D models, I have a couple of slides at the end comparing the two. When I deal with full 3D model, now I'm going to say every place, everywhere inside the formation will have an effect on the fracture everywhere. So that it becomes a lot more sophisticated and more difficult to solve. Yeah. At UH as well as in other places, everyone that developed his own models basically for research, and we did the same. So if we deal with plane strain, which is very good in explaining a lot of things, and we use it in data analysis, simplifies things, but it also gives very good results. We're saying all the stress and the resulting strain remain on a plane which can be repeated infinite times. So every plane is by itself. And you can look at it either vertically or horizontally. If you look at it in a vertical plane strain, and then the model that was developed years ago for that 2D model, which we are going to use in analysis of data, is Perkins and the Kern model, the PKN. And the horizontal plane is KGT, KGD, we used to call it Kirsanovich and Zoltov model, the original name. That's saying I do it in the horizontal plane. There is evidence that PKN works better, and I'm going to explain why that's my own personal opinion. Of course, other people may disagree with it, but I'll tell you why I think this is the case. So if I look at the basic PKN, in a regular class, we'll go through modeling and writing equations and maybe software for it. For PKN, I'm going to assume that that the fracture cross-section is elliptical, and as it is constant, the height more or less, although we'll allow that to change, and is elliptical in the horizontal direction. And from there, I can write an equation for width, and I can write equation for pressure. And the equation for pressure is going to show that with PKN model, pressure, if I don't have sharp increase in heights or changes, serious changes, in most models, when you see some increase in pressure with time. A KGD assumes that I have a rectangular shaped cross section, essentially saying we have slippage on the boundary, and that will reflect into constant pressure or even declining pressure. In most cases, in field cases, we have seen that the pressure does, when you have a successful job, pressure does increase with time a little bit in some slope. We'll get into that slope in just a few minutes. Well, to tell you, it's between. No, I need to wait till because I need to talk more about it and see what we plot there to see that pressure increase. In those cases, we're looking at fracture height and fracture height prediction. We is containment important? Yes, it is important. I'm going to show you some experiments that we have done in the lab before. Is it critically? Absolutely. You can, if you don't watch for it, you don't want to fracture into water. If you end fracture, say, propagating downward and fracture into water, like some of the shale formation in northern US, United States, you watch very much for fracture height because you have water zones below, and if you fracture into water, you essentially have a water well. So you want to control it. And it's not only that you get too much water, but you waste the propellant and the fluid. Can it be controlled? Passively that has been usually successful by looking at the injection pressure and monitoring what the pressure you're injecting. You may be monitoring the job. There is some ways to do that. We'll talk about some of them, but that's in a passive way. So I don't want to exceed certain pressure, so I don't break into another zone. Some people have tried it actively using, say, if you have downhole, you have a zone below your pay zone, and that is maybe carrying water, and you don't want to get into it for water or whatever other reason. You could. Some people have used the heavier propellant. So they say, well, the heavier propellant will settle and will prevent the fracture from you end up having very high friction pressure in order to propagate that fracture. So it prevents a further propagation into the lower zone. People have done it by creating a fracture with propellant and then going back, perforating above into the pay zone and doing the fracturing, so it may work okay. There is the success of those active using propellant is not completely proven. Passively, yes, it's proven by, especially when you monitor what is going on using temperature, behavioral pressure to know whether you're propagating downhole or not. You go propagating downward or not. The containment happens due to one of the natural containment happens because if you have a stress contrast, if you have a change in lithology. Let us show some slides, some experiments that we did several years ago on that subject. First, to stresses, it's very important to in advance to calculate the stress both in various layers and to calculate or measure the stress in your pay zone, above the pay zone and below the pay zone. If Many times the stress variation is just due to variation in Poisson's ratio. If you don't have lithology change, but it can be due to just a change in Poisson's ratio. If you remember, we talked about this upper equation here, and this is the effective stress in horizontal direction is Poisson's ratio over 1 minus Poisson's ratio times the effective vertical stress. If I substitute the definition of effective stress with Boyd's constant, I end up having something like this. So if my Poisson's ratio, I decided to, I did not write it as a slide here, but I did a little bit of calculation with saying, okay, and maybe you should give you this as a homework assignment. If you have sandstone and Poisson's ratio is 0.25, if I have 6,000 foot formation, I could end calculating my horizontal stress if I assume 1 psi per foot for vertical stress, for total vertical stress, and we substitute all the Boyd's constant and pore pressure. We say pore pressure is gradient, say, of here I said of 0.4. I end up calculating vertical stress of 6,000 psi, horizontal stress of 3,600 psi. But if this pay zone is surrounded by shale that is softer, and let's say Poisson's ratio in this case is 0.4, and then my horizontal stress will be calculated at 4,800 psi. That is 1,200 psi stress contrast between the pay zone and the shale zone. And if you have something like this, that will be sufficient to confine the fracture. So let's look at, here is the problem. You will have it, you can solve it and see whether I made a mistake in my calculations or not. But here what I'm trying to show, if I have soft shale around the pay zone, sandstone reservoir, it may be confined. Well, let us see if it's really confined or not, because we'll talk about theory. Here is an experiment that we ran several years ago. This was a piece of rock that was 18-inch in length. It was 12-inch in height here, and the thickness was 6-inch. And we created a well in the middle. We had a perforation like you see here. I hope you see my mouse, around the mouse. So you can see here I perforated or have this an open area, and the rest is closed. I have a pipe here. And I started injecting, and you can see I created very much the fracture that I have here. The reason for that is I've got, basically I did not stress in the middle here, and I put 1,200 psi above and below. So I have a stress contrast of 1,200 psi. That was sufficient to confine the fracture, although the formation is homogeneous, and there's absolutely no change in lithology between the middle part and the upper and lower parts of the rock. This was the same piece of rock. The only difference is the stress. So we applied vertical stress of 1,400 psi. I applied side stress here of 2,000 psi, and then the stress perpendicular to the screen is 0 in the middle, 1200 above, 1200 below. So those are the lowest stress. So I'm expecting a fracture that will propagate along the screen. And you can see here, if you look carefully in it, and hopefully you can see it, you can see it looks like almost like lines here, like streamlines, where the fluid is going in and opening up this fracture. Experiment looks really impressive. Well, in the other case, if I have negative stress contrast, if I say, okay, maybe I have sandstone here, I have shale, maybe I have water, although I may have a barrier here, but below the shale, I've got low stress formation, and I don't want to get into it, but we did not realize that, so we fractured it anyway. So this is a similar case, a similar size rock, and you can see here the smallest stress or smallest stresses are the one perpendicular to the screen, and you can look here. This is just a highlighter, and you can see it basically to compare the size. This is 18 inches again, and 18 by 12 by 6 inches in thickness, and here we're doing it in fraction in the middle. So I have 600, 1,000 psi, 1,000 psi, and I have here zero stress. So what happens here when I fracture in the 600 psi? Initially, if you see that same piece of rock, fracture propagated very much like what you would expect, but once you saw the low stress, you can see the propagation went downhole. So went downwards, and boom, all you can see, much of the propagation went into the lower stress. So one has to be very careful. So knowledge of stresses is not just something, the theoretical thing you need to do. It is really practical thing to do. This is the reason people been have been measuring and calculating stresses. We talked about calculating stresses from logs, like the equation we saw. We're going to talk about measuring stress. Well, part of it, that fracture closure pressure, if I don't inject very much fluid and I monitor the pressure carefully, I will see the fracture closure pressure. It's a very important parameter. We are doing a lot of research in the area right now. Believe it or not, it's still not a is still open for interpretation. So we have our own technique. We may mention it a little bit. This is more of a research area, but we have companies really believe in what we're doing. So there's still a lot of work to be done in the area. Nothing is final. Science and technology never stop. But the important thing about this slide, you can see here, it went down all your much of or most of your propagation is happening in the lower stress zone, and it ended breaking even into that this lower higher stress zone. So what is the problem with that? The problem with that is your perforation are up here, your propant may be sitting all down here. So you may not have communication. Even if this zone is productive, there is no communication with the perforation. It is worse if this formation is having water or having issues, or so you're wasting a lot of energy, a lot of money, your propant, your fluid, and to get a fracture that is not effective. So you fracture it and say, oh, I am not producing nearly as much as I expected. Well, maybe because the fracture went in the wrong direction. I saw the opposite too. This was not in the slides, but I saw the opposite too. We've been involved in a case for, can't tell you the oil company, but here in a smaller oil company in the United States, several years ago where they fractured, and most of the fluid it came from a layer that they did not know was productive. And the reason for that is the fracture propagated upward and intersected that formation that they were not intending to fracture. At the end, luckily for them, they ended getting a lot more production than they expected. But still, that's not right because one has to know in advance. You need to make at least some knowledge of what is going on so you design the best fracture treatment possible. Well, if you have some lithology change, you could have problems too. So a situation like this where there is a fracture that's propagated upward and it ended since I have a barrier here that's not very strong. The fracture, although there is some breakage through it, but most of the propagation went sideways. So that's again another issue. This is more of discontinuity. We have seen that actually. I have a case that we wrote a paper on several years ago. If you're interested in it, we had the logs, we had everything, and we ran very nice design, and we said, okay, we'll go apply it in the field. And after we applied it, we found out the fracture height, actually the fracture was better than expected. So we go back and measure it, and the fracture height was smaller. And eventually we realized that the logs did not show some break in lithology. So once you have a break in lithology, that can be a barrier. So you end up have confined fracture. So this is something again we did not know. There is people have seen, especially in shallower formation. This from paper by Warpansky. It was a fairly shallow formation that they went back and mined back the formation. You see were multiple fractures. Part of it, this can be misleading a little bit because formation was a little bit too shallow to have the stresses that basically overcome heterogeneities in the formation. So the fracture followed the heterogeneities. You see things like this when you fracture shale. Because of the natural fractures, you end up opening those natural fractures, and they have very significant effect on what is going on. We are going to see some cases, real cases, actually with deep formation here in the United States, shale formation that we analyzed using some technique that we have developed. This is multiple fractures. There were actually, this also from Warpansky's paper, but there was a recent paper a couple of years ago by ConocoPhillips where they did something similar, but except that they did not mine back the well because that was too deep to do that. Here we're talking about couple of 100 feet. But in ConocoPhillips' situation, it was a very deep formation, and they did not find proppant in where they thought they would have proppant. So fracture propagated in we have multiple fractures in multiple areas. It was a horizontal well. This one here, it was a vertical well in this example. You can see here also, you can see the fracture propagation. It looks like it jumped. Obviously, it went around here, and then there's another crack. So there is discontinuity in the fracture. And anytime you have turning of fracture, that's usually not good news because it have very high friction pressure, and the turning around of fracture happens on steps. And so it does not happen very smoothly, and you would have a very narrow effective fracture width, which usually can cause sand out. The sand out meaning that the sand cannot continue to move. Its friction pressure is so high that basically eventually you have to shut down the treatment. So here I'm going to give you some equations that were published in literature. There's so many different equations looking at things like that. And so here, if I have stresses, you can you can see uh, if fracture is propagating through higher stress, it may give you a pinch point. It may go up, and if I get higher stress here, I may have there'll be an upper tip and lower tip, and with a pinch point. So let's look at what would it would take to propagate a fracture. Usually we do it numerically. There is a lot of simulators in commercial as well as research simulators for fracture propagation. But sometimes it's good to look at cases where you have an analytical solution and you can look at it yourself in case you want to do something very quick. So in a situation where this is symmetric case, I have a zone like this, a pay zone like this, and surrounded by a higher stress. And here, since it's symmetric, I'm going to assume sigma 2 and sigma 2 here, they are same values, same rock, and I have this pay zone in the middle. So if this is the case, if I ignore the effect of height, there is a little difference in height, so nothing is really truly symmetric, because even if if the stresses are the same, there is hydrostatic head that is different. But here I'm going to ignore this effect and say fracture propagates upward and downward similarly. So I end up having a saying, well, the pressure, I can calculate the pressure that I need to in order to fracture this formation. This pressure is related to the stresses that I have above and below and in the P zone. So since it is symmetric, sigma 2 here, pressure sigma 1, and you can write this equation. I usually give a problem in this for people to see what happens when the fracture height is very large. Once it gets very large, the effect of KIC becomes very small. So this confirms what we talked about early in this lecture. If it's when height is very small, and then KIC becomes important. So the importance of this second term, it gets smaller and smaller with time. With fracture propagation and height, eventually it becomes essentially negligible. If you use this equation, please remember when you write something like this, it is not in degrees, it's in radian. I've seen students that put this, get the angle and write it in degrees and say, well, the answer doesn't make any sense. So of course it doesn't make sense, because this should be in radian, not degrees. If I have a case that's not symmetric, it gets a little bit more complicated because the propagation in height above and below is different. Basically, the center of the fracture moves, in this case, upward, because the upper layer stress is smaller. So I'm expecting more fracture propagation in upper zone than the lower zone. So you end this equation, and I'm just writing this equation for your knowledge as something to use. But you're going to find many equations like this in literature. So here, if I have non-symmetric case, even if KIC is all the same, 1,000 psi per square inch, you can see that the center of the fracture is moving upward. It can move actually upward above even the pay zone. Depending on stresses, depending on your treating pressure and dose time. So let's look at the material balance variable. This is the variable here I'm injecting. You have fluid leak off, is widening the fracture. And I want to look at this in general and say, well, what happens, how we can analyze data. There was a paper that was written, a bunch of papers were written, but there is one written by Multispin that we are going to depend very much on the first part on this analysis. Then we'll talk about the paper that myself and my students, actually multiple papers that we wrote on the subject. Most people don't realize that many of the models will depend, and the analysis techniques will, during fracture propagation, will depend on what is called the power law assumption. Basically, it is saying fracture length, and here in area, we're writing in terms of area, but if you assume that the height does not change very much, then the length is function of time raised to some power. So if I take this concept and going into treating pressure analysis, and I need to refer you to paper by Nolte and Smith that was published several years ago. I should have written the paper number. I thought I did. I'm sorry. Let me see. I did not write it. I apologize for that, but I think we need to. Well, I'm going to modify the presentation before putting it into ResearchGate to have that SPE number, because this is not just to make sure that I'm referring to the right place, but also it is interesting for you if you want to pursue the subject to read that paper. It's very fundamental paper by Nolte Smith, and it was published a long time ago, but it is really an excellent paper. Basically, they said, okay, if I plot the net pressure is the pressure you're observing, the downhole pressure minus closure pressure or minimum in situ stress. If I plot that net pressure, and you please notice when I say net pressure, that's a pressure difference from minimum in situ stress, not pore pressure. People that are doing well testing, the delta P is from pore pressure. So here, my downhole treating pressure minus minimum in situ stress. If I take the log of this value and plot it log of time, they said, hey, we can get one of various modes, and they called it 1, 2, 3, 4. Okay, let's look at this modes. Mode 1, which I see pressure going maybe between 0.2 to 0.35, although I'm writing what they wrote, but I think it's usually a little higher than that. So if I get slope like that, that tells me that the fracture is propagating normally, because that's what I expect to see from that power law model. If everything is okay, I'm going to see about 0.2, 0.25, 0.3, 0.35, in that range. That will tell me that the fracture is basically fairly confined. So I have some containment. There may be obviously some fracture height growth, but it cannot be excessive at all. And so that's what you would hope to see throughout a fracturing treatment, obviously, because now you see a nice fracture is propagating, you're getting a lot of length. Okay. Then they looked at model 2, and they said uncontrolled fracture height growth. That's when I'm going to differ from them later on in what you're going to see in a minute. And they said, now you have an issue, and many times it may be natural fractures, and you may it end turning into mode 4, where you say, okay, my mode 4 is, let me go to mode 4, pressure is declining. I added this intersecting or opening natural fracture, breaking out of zone, lower extension pressure. Actually, in their paper, if you read their paper, Model 2, they had an issue of explaining Model 2. We have a different way of doing it right now. Then Model 3, nobody disagrees with that, is saying if I see very sharp pressure increase where it goes to slope of 1 to 1, that is usually screen out. So you better be ready to stop injection. So that's tell me that the fracture is ballooning, is getting wider rather than getting longer in length. Sometimes you see cases where it is even going higher, the slope is higher than 1 to 1. Okay, so we look at that, and we there was some recent decline in use of this model because there is a mode 1 and model 3. There's really no disagreement in them. 2 and 4 were some problems. So we developed our own new technique. So here I'm referring Multispin technique. The one issue that we had with it is the reference point is all based on 0 time, which is the start of injection. We look at some experiment that we have done in the lab and some observation in the field, and we think that fracture does not continue propagating. And once it stops propagating, everything as if it's the time is reset. So we say the process that's in the technique we developed when the process is discontinuous. So we build another approach. I'm going to go through it a little quick because it's mostly a research area or very recent area. But I encourage you to read the papers. We wrote few papers on the subject. It's very interesting. So here we took a case and we applied Nolte-Smith analysis. And this is taken from this paper here. And this paper will give you reference to Nolte-Smith. I should have done it anyway. Sorry for that. And it looked something like this. And when you look at it, the early part looks okay. But then you can see now it's going, the net pressure, this is log graph. The net pressure is flat, but if you are analyzing the data, you say, well, I'm not going to do anything. And I do not know what is going on. And then you get in here, you have to wait till this is 10, 20, 30 minutes. This is what people call frac pack. This is fracturing high probability formation in the Gulf of Mexico. We got it from a company that did that work. So, but all I can tell you is in Gulf of Mexico. So basically they waited, this is 30, 40, after 40 minutes of injection, usually those runs are usually fairly small. You stop. So we analyze it using our technique. Our technique is saying every time there is some changes, I reset everything. I reset the reference point. So we call it moving reference point technique. So the reference point is not always 0. And I don't use logarithmic. I'm changing this and I'm plotting my exponent versus time. So here, this area here, the green is saying I have fracture propagation, and the red is saying I have a sandout. So this is telling me that fracture was propagating okay here. There was some issues after about seven, about 7, 8 minutes in fracture propagation. Actually, I don't have as much propagation as I thought I have. And then it went back into normal propagation, did the same thing. Then I have normal propagation here, not opening natural fracture or anything. I have normal propagation. And then at this point, I started seeing movement towards send out. And here I know we are in trouble. So many times in frac pack, you don't stop as soon as you see evidence of send out. You continue to inject. The reason for that is because the formation is very high probability. You want to create very wide fracture. So the area, the early area, you call it your fracturing. The later area here, you are still injecting to widen the fracture or to pack that fracture. And this is the reason we call it frac pack. Frac pack is a commercial name for Halliburton. I use it because I worked for Halliburton for 30 plus years before moving to academia 10 years ago. So, but some others will call it frac and pack. So there is various names to it. But here you are widening that fracture. So many times people continue to inject. They are aware of it, that is it in sand out mode, but you continue to inject anyway because you don't want to get narrow fracture, you want to get a wide fracture because you're dealing with high probability formation. And this is another example, and where I saw decline in net pressure here, and I see in this area there's actually, it seems like we propagated in height or intersected natural fracture significantly before we moved into fracture propagation. And so this was a very different situation from what we expected before. And we went into the packing of fracture for most of the fracture treatment. Then we applied it to shale formation. We applied it to two cases, one Marcellus shale, that's both are in the United States, and one was the Eagle Ford shale, also in the United States. Eagle Ford shale is produced a huge amount of oil and gas. So and that was an interesting situation. I'm not going to go into much details on how we did it, but the interesting thing, it was more or less like a blind test. And we can see here this, every time you intersect a natural fracture, it dips. So we say we have natural fractures here, here, here. So in those areas, I can see very clear natural fracture. You pass the natural fracture, and then I end getting into the fracture propagation. If you propagate the fracture some distance, and boom, you intersect swarms of natural fracture, and you can see it right away. So that, to me, that was, if you look at it, let me see, I don't think I applied the Multispin technique to it here. For the Eagle Ford shale, I saw similar things. And you can see here again, I have the intersection of natural fracture. After some time, most of my fluid is leaking into natural fractures. So after, this is 190 minutes, you know that you're no fracture propagation anymore. You're just leaking off, the fluid is leaking off into natural fractures. So if I'm running the job, I say, well, at this point, I need to stop the job. Let me look at usually going back to regular fractioning treatment, what do? You in a typical treatment, that's what you do. And although things have been changing a little bit these days, you you have you have a pre-pad basically to initiate the fracture. Pre-pad usually is a lighter fluid, and you are initiating the fracture, and you follow with the pad, which is basically fracturing fluid, except it does not have propant. So you want to widen the fracture to get it ready to bring propant in. You want the fracture to be a little wide when you propant going in, otherwise it will sand out immediately. I've seen a case where where we're using 100 mesh sand, and since there was not enough pad or pre-pad, the fracture sanded out immediately. You don't want this to happen. So you inject the fluid, you open up the fracture, you widen the fracture, and then you end putting propant carrying fluid. You may end with just again fluid without propant in order to displace the treatment deeper into fracturing. You clean the wellbore, and sometimes this works, sometimes it doesn't. This will that would take a lot of time to discuss, so I'm going to leave it at that. So, what's your fraction material? You have propant selection, you have fraction fluid, you have additives, and you have fluid testing. So we'll touch in each of those a little bit, but you will have the presentation. You can look at it, and if you, I have actually a lot longer presentation that is goes into all those aspects in more details. And I'll probably, what I will do, I'll put the longer presentation on send you the PDF file. May not cover it here, but will give you the presentation anyway. So let us for propant is important to provide the necessary conductivity to produce the formation. If you remember, I put this equation again. If you remember, I told you always to remember this equation if you work with fracturing. It's important to have fairly decent fracture conductivity. So you want to get to good dimensions fracture conductivity, and this dimensions fracture conductivity is Kf, which is coming from the propant, the width of the fracture, which is what you injected for how long, and what the pressure is, formation probability, and the fracture length. So you want to get the decent I'm talking about. Our recommendation always was 30 for this value, but higher or lower, even if you have lower value, it will work well. But you want to make the design because you lose conductivity with time for multiple reasons. So you need to have propant that will give you that upper part here, the probability times fracture width. So that fracture conductivity. You don't change probability. You change the flow regime inside the reservoir. So where do you get this information for fracture probability? Well, you get it from testing. But you know that conductivity will decline with time. There is closure stress that may crush the propant. This propant will not last forever, especially if you have cycling. That is very much, that's like when you when you study metals, you talk about fatigue in metal. So the cycling if you produce, you increase the stress on the propant. If you shut down in production, then the pressure builds up, so you reduce the stress on the propant. So you keep going. The cycling will cause fatigue to reduce conductivity or probability of that propant. Embedment part of the proppant to get embedded into the formation. They are not infinitely stiff, so there is some embedment inside from the proppant into the formation. Well, that obviously will reduce the fracture width and reduces fracture permeability. If you don't have the right fluid and the right breaker in the fluid, then there can be gel residues that plugs the fracture. Hopefully you work with your service company or you avoid problems like that. So this usually not an issue. If an issue, then somebody did not do his homework. The fine movement can plug a fracture. While people have developed fluid, this is a big another subject, fluids, where you it seems counterintuitive, but people have added fluids to propellant is like it's almost like paint over the propellant. So covering a resin coated sand where it hold the fines rather than let the fines move through the fraction. The you would think it's better for the fines to move. The only problem when they start moving, they get they get held near the mouth of the fracture, that's near the wellbore, and that's a disastrous thing to happen. Another issue is diagenesis, basically degradation. If you this is physical and the chemical degradation. It's people that work in welding, they know that when you have two different metals side by welded to one another, you could have problems there. It's like if you don't treat your battery properly, you end up having a lot of junk built on it. With diagenesis, is something similar. There is electric current in all formations. This is the reason you do electric logging, and it we experiments have been run, and you leave propellant in a fracture and water, depending on the composition you have there, and you can come back a month later or 2 months later. It doesn't look like a fracture altogether. There was very interesting presentations on the subject that I'm not going to get into it. But the diagenesis is very much what when you have a limestone suffering from diagenesis and losing its old permeability. This is the same becoming dolomite. So that's a diagenesis issue. So it is a real issue. So there is all of that can lead into conductivity degradation with time. So you will see graphs like this in industry. You get it from those are published. There is a bunch of labs that have done those experiments. You can see you plotting conductivity in Millie-Darcy fluid versus closure stress, and it depends on propellant concentration. The higher propellant concentration, the higher the fracture conductivity. But as the closure stress increases, the conductivity declines. So this is function in this if I'm using one type of propellant, but also it depends on the size of that propellant. So there's multiple cases. So the first case we talked about the concentration. Here I'm talking about the size. Here is 12-20 mesh. That is the biggest one. This is the 2040 is the one in most sandstone formation. 2040 is probably the one that's most commonly used. Sometimes if the formation is fairly high probability, you may till in with bigger propellant to make sure that the fracture is open at the mouth of the fracture. You don't want. It also depends on the type of propellant. Here, when I use Ottawa sand, and when you talk about sand, just want to attract your attention, it's not sand you find on the beach or find in the Sahara. Those are sands that are mined. So they have not been exposed to atmosphere for millions of years. So the sand that's exposed to atmosphere for many millions of years, they are cracked and they are very weak. So they are not spherical. So they have a bunch of issues. So when you talk about the sand, natural sand is being used, is usually, it's always actually, not just usually, it's always mined sand. You mine them from underground, and then you sieve them, spread them into different sizes, and so on and so forth. But there is also man-made material, bauxite, for example. Bauxite is aluminum oxide. You can have, it's a lot stronger. So if you have very deep well, if you have shallow well, you may use natural sand. It's cheaper to use. As the formation gets deeper and deeper, then you need to use stronger and stronger propellant. Otherwise it will crush. There is some formation in the Gulf of Mexico that is almost 6 miles deep, with pore pressure of 20 plus 1,000 psi. So that's extremely high. So you have to fracture it, and those are. I was involved in some where we designed some fractures for them, where uses a very special propellant and it requires special procedures to work with. So as the formation gets deeper, higher pressure, you want to use better, stronger propellant, maybe bigger propellant. And so this is kind of a schematic telling you what kind of, depending on the closure stress, what kind of propellant you would use. So very much the summary of what I said is lower stress, you may want to use sand. As the stress gets higher and higher, you want to use a stronger and stronger propellant. There is actually a propellant right now. I'm not going to mention the name, it's commercial products, but they try to produce propellant that is more spherical and one size. So instead of saying 20/40, it says only 40. So it is uniform size. The uniform size will give you a higher conductivity and also give you a higher strength. There is a very, very good paper, interesting paper by this gentleman, Terry Palash. SPE number is given here. I asked him to provide me some slides, so he sent me all the slides. I'm just going to use a few of his slides there. If you want to get more into propellant, I suggest that you read his paper. Really, really excellent paper. He's talking about the crushing tests, because in order to get this conductivity, you need to run a special test. So he went through all those testing. He was for carboceramic, at least he used to. And he said, usually those are the assumptions, that the crush test simulate realistic condition, everything is reliable and repeatable. The width does not affect crushing, experiments uniform packing, and he has slides to show that none of that is really true. So you have to be careful in picking up. So he ran experiments and found out that first, that's the procedure they do. It is the equipment they used. And it said we'll work with it before and after. He found out are the results repeatable? Not really. You can see in cases here, there's a big difference in the results. Some are good, and some are good. The difference is very small, but there is some that are from one test to another. Here you're saying test 1, 2, and 3. From 1, 2, and 3, there is a big difference. It can be up to 50% change. So sometimes you have to take this with a grain of salt. I think pinch out can be an issue. Probant pillars, although sometimes we're going to see people may design for probant pillars. So you don't really have as uniform packing arrangement inside the fracture as we think we do. This is one reason when you analyze data, it may not behave or did not give you exactly the results you think you achieved. There is other designs. Now many people, instead of at least a few years ago, or started looking at, hey, instead of trying to get uniform packing in the fracture, maybe doing something a little different. One of them, like partial monolayer. Partial monolayer meaning that I have sand, and in between, one layer of sand, in between there is nothing at all. It's just the fracture is open. If you remember the equation that I showed you last week in the fluid flow part, I'm showing you equation of fracture that is open. The probability of an open crack is basically infinite. It's extremely high probability. So that's the idea behind partial monolayer, saying that if I have propant that is keeping areas in between extremely high, so the average is going to be very high probability. Well, yes, that is true, but this works only when you don't have very high stress. Because if the distance is very large, the fracture will pinch out in between. You end up having no conductivity whatsoever, no permeability. So you apply those techniques with is not just one solution fits all. Pillar frac and the highway frac, and conductor frac, they're all the same thing, and that is this with names given by different service companies. Basically saying pillar frac is a very old idea. It's similar to partial monolayer, except you're saying, well, I do have multiple layers inside the fracture, and in between, so I have a pillar and pillars, and between the pillars I have basically empty area, so open fracture. So the average is very high probability. And it actually, I've seen results in more than one country in one place, and you can't argue with success. They do work well. The production was a lot higher, at least the initial production. The one thing one has to worry about is to look at the long-term production. So make sure that you don't have sharp degradation or closure pinch out inside the fracture. This is one case that I have seen. This company ran this case in Eagle Ford and said, hey, they did it using one of those fractures. I think it was a conductor frac. And it saved 1 million pounds of propant. But the one thing one has to remember here is also it's an Eagle Ford. So the production from natural fracture is very important. And the formation itself has very low probability. So you do not need really a huge amount of propant. But this with the conductor frac where you have 30-second burst. So your system is, the injection is set to have burst every 30 seconds of propellant. It did, at least the claim that it did work. It produced at least as much fluid with saving as 1 million pounds of sand. Fraction fluids, you want to get it, your fraction fluids will give you viscosity that controls weight, that impacts the transport. You have control fluid loss, so you build a filter cake, very much like the mud cake that you see in drilling. In drilling, you want to build the mud cake to prevent drilling fluid to leak into the formation. Here, you do similar thing. You filter cake, so it is a similar concept. So you lose a little bit of fluid, and it builds a filter cake, so it prevents further loss. It provides some density that gives you a hydrostatic head, and also it helps in settling of the fluid. Both the viscosity and the density will help in settling, controlled settling of propellant. Friction pressure, you want to reduce friction pressure, otherwise this would be horsepower that one would be losing. And you want to control cross linkers. You want to make sure you don't damage the formation. This will get into it in a minute. Fluids, when you look at fluids, I'm sure that all of you know about that. I have Newtonian fluid. Basically, if I plot shear stress versus shear rate, if I have Newtonian fluid like water, then it's a straight line. Basically, at zero shear stress, I have zero shear rate. There is no movement, and it follows linear behavior like this. The slope of this line is your viscosity of the fluid. Okay. In all industry and fracturing, you are not using Newtonian fluid, you're using non-Newtonian fluid. Non-Newtonian fluids can be different types. One is Bingham plastic, which it takes yield stress. So there has to be some stress before the fluid can move. And this is important to make sure that cuttings do not drop to the bottom of the well when you stop circulating. Otherwise, it becomes a huge issue. And then from there, it can either follow up, the fluid follows a straight line, it'd be like Newtonian fluid, or it could be actually even a curve. For the non-Newtonian fluid that we use in fracturing is the pseudoplastic. So it's a curve like this where we say shear stress is equal to some constant times shear rate raised to some power. We'll write the equation in a minute. So it is equation of a curve where that power, which n prime, is less than 1. So let me show you the equation here. This is the power law equation. This is constant K prime times shear rate times to the power of n prime, when n prime is less than 1. So here, so what is the viscosity of this fluid? Well, actually, there is no viscosity. There is an apparent viscosity. So you can see as it gets, I'm going to I'll show you equation for apparent viscosity, but the apparent viscosity here is basically, if I want to get the apparent viscosity at this point, I draw a straight line down to 0. So you can see that the straight line gets flatter and the flatter as the shear rate gets higher. So that is shear thinning fluid. So it acts as a as a lower viscosity fluid as the shear rate gets faster. So that's what you use in fracturing fluid. And this is opposite to dilatant. You do not use dilatant in fracturing fluid. A dilatant, the exponent is larger than 1. So you can see that the shear rate, as the shear rate gets larger, the apparent viscosity it gets higher. And so here is what basically this is the equation for the model, and the apparent viscosity here you can see for fracturing fluid, the apparent viscosity is the slope of this line. So as the shear rate gets larger, the, the fluid behaves as if it is thinner. So it's a shear thinning fluid. And the equation for apparent viscosity looks like this. Many people think it is the tangent. So please make sure you understand that it is the line going from zero shear rate to that point. So if I have linear gel, water, the N prime is 1. This is the K prime, is that value. The viscosity as you put it in this little, you apply the shear rate to it at shear rate of 170 inverse of a second. Water is 1. Basically, the viscosity is constant. It's 1. Linear gel is N prime is 0.8. If you have cross-linked gel, we're not going to get very much into that. The N prime can be as low as 0.5. So the requirement, we're running out of time, so I will just to show you those. It has a lot of requirements. One of them is it has to be cost effective, of course, but you want to maintain viscosity. You want to maintain viscosity, you want to have the fluid to keep the propellant being held in place until you try to close that fracture. And you want to be able to adjust this viscosity. You see, this is, I will let you read this requirement. There is water-based, like what we discussed before. Most of the fraction fluid now is water-based. At one time, people used a lot of energized fluid, nitrogen, CO2, or a mix of the two. This is the foam-based fluid. It's not used as much. In the presentation I'm going to send you, I was going to tell you why. Essentially, although foam is very good in carrying propellant and transporting propellant, does not apply very high hydrostatic head because it's mostly air. Foam does not have much hydrostatic head. So it has a special application. Oil-based fluid is it's still being used, but it's not as popular because of potential risk factor. And people have used the acid. We use the acid a lot in fracturing carbonate fluid. We're not going to get much in. So linear gel, there is different kinds. This I will leave it up to you to read, especially chemical names like this is not that easy to pronounce. But we have used the acid fracs and acidizing in general. We actually spend in the regular class, we spend some time on acidizing because it can be very important, especially in carbonate formation. There's even acid has been used for sandstone. You could acidize sandstone formation. However, when you acidize sandstone formation is essentially to remove damage. For carbonate formation is to create wormholes or improve average permeability around the wellbore. Cross-linked fluid, you want to use it when you have high propellant concentration. If you're fracturing shale, you probably do not need to do that because you do not need to use much proppant concentration at all. And cross-link fluid can be different types with uh, some of these heavy metals are being frowned upon right now. People don't want to use titanium, zirconium, or even aluminum. You now there's a lot of move towards using organic cross linkers. I know we got involved very much into using organic cross linkers for for conformance fluid, and same thing applies to fracturing fluids. Uh, so the cross linkers, depending on what you use, titanium, of course, is it is permanent, shear sensitive. It can be variable. There's a lot of decline in using things like that because they are cancer causing agents, and many places actually prevents you from or prevents service companies from using heavy metals in fluids. Energized fluids, we talked about it already a little bit. Um, it's it was more popular in 80s and late 80s, basically for reasons for carrying propellant, and if it's not very deep formation, there is very low leak off, so it works very well in this situation. So here basically is loss control, is carrying ability, but the biggest disadvantage is lower hydrostatic head, and it may have very high friction pressure. In models, now I have people will we used the 2D model years ago. People now do not use 2D. We use 3D and the full 3D models. You can look at it. 2D models is people stopped using it for a very long time. It's basically because of computers now are a lot more sophisticated. You can run models very fast. Both the pseudo 3D and the full 3D models. The full 3D models have the advantage of looking at layering system in more complete way. So that's actually what you want to use is the fully 3D model. It gives you maybe better picture of what is going on. Pseudo 3D model, although it may look at stresses, but does not look at the layering system and what is going on really accurately. Very similar to the fluid flow models. You want to fluid flow models, you want to look at 3D model, looking at what is going on the effect of each layer accurately, rather than approximating that behavior. So lately, everybody has been working on the fully 3D model. Starting the mid 90s, the use of 3D model has mushroomed. Even at University of Houston, when we're developing models, we developed the full 3D models because you want to look at stresses more accurately, you want to look at layers more accurately, you want to see these effects and design your fracturing treatment. So 2D models is not being used. I need to remove it from here. Pseudo 3D model, there's two different types. Some are they use cell model, but the ones that you really want to be using is fully 3D model to calculate height, width, and length correctly. A pseudo 3D model, there's a lot of assumptions where you really don't calculate the three, although they pretend to be calculating all those models, but but it's with a great deal of assumptions. So that takes care of the presentation. I'm going to put in, I put it in ResearchGate, and I'll send the link to Dr. El Garhi, where you can download this presentation. What I'm going to put on is going to be a little bit more expanded presentation.
Thank you, Dr. Soliman, for a very informative webinar. I'm sure the audience has benefited greatly from it. In the meantime, I've collected a few questions for a quick Q&A session. What are the reservoir parameters we can get from the square root of time technique and the G function?
Okay, I'm going to cover the G function next week. So a G function does not give you reservoir properties. It actually gives you leak-off coefficient. There have been techniques that were developed to analyze the data, the same data, to get formation probability. I will go through those techniques. We developed our own techniques, as well as there's techniques and literature. We'll cover all of those next week. So maybe we will need to wait for next week to talk about. G function is very important, and we'll cover it. There's some advantage, disadvantage of using G function, but we'll discuss it next week. So that will be an incentive for you to attend the next week.
The second question is, how can we solve an issue of propant flowback near wellbore?
That's a very good question. And I have seen this issue many times. We actually working on, we have a PhD dissertation, the student that's working on an issue like that. There was always suggestion that you tail in with maybe resin coated sand. One thing is not to follow the treatment with water or with the non-carrying fluid. So when you have probant moving into the wellbore, you're being replaced by probant deeper. But having resin-coated sand or some treated propant is probably the best idea. You could allow for fluid to leak off for a short time before you start flowing back, because I need to mention that you want to do some flow back to close the fracture, because you don't want to wait for forever. So if you have resin coated propant or similar, there is multiple types of fluid. There's some use fibers, for example. That's another commercial techniques. So that will allow the probant to be sticky near the, if you till it in with this type of propant, it becomes sticky near the wellbore, so it allows only fluid to move in without having the propant moving back. But that's always a big issue.
Another question is, which size of propant is commonly used with shale fracturing?
Most of the propant I've seen was essentially sand. I know that various types of sand, like Brady sand, which is not being used anymore, but you do not need huge conductivity in shale. The reason for that is, if you look at that equation, formation probability is very small. So you do not need very high fracture conductivity. Sometimes people would tell you that the mere fact that you open up the fracture, the the just the grains from the formation will give that fracture high enough conductivity. I always recommended that you use some propellant. So people, I believe sand is the most common propellant used in there. But that's a good question. I will. Things keep changing. I will double check on it and I will let you know next time. But the cases I've been involved in was mostly sand. I'm talking about for shale.
Another question, Dr. Solomon, you mentioned KIC and HS. What is the relation between them?
Between KIC and what?
HS?
HS.
Yes.
What what is SHS?
I'm not sure. The question is.
So maybe he means horizontal stresses, for example.
I I don't know what is this. When it's stress, you say sigma. We talked about later on in.
Dr. Solomon, because he is writing and he cannot have the Greek
Oh,
letters.
he's
So maybe
talking
he mean
about.
horizontal stress.
No.
Okay, this one.
Yeah, he's talking about height. Okay, this is formation thickness. H is formation thickness. HS is the penetration of the fractures into the upper and lower zone. So if I have symmetric case, I'm calling this HS. This is actually I ended calling it A and B in the next equation. There is KIC is a property of the rock, not of the fractures. Is a property of the rock. So when we looked at it in sandstone, we said KIC is 1200 to 1500 psi square root of inch. So that's property of the rock. That is the value that the fracture has to overcome in order for it to propagate. So in this case, the stress intensity factor, not the critical factor, it will be the pressure inside the fracture P times this whole thing, which would be H over 2 plus HS. Okay? So if this value, the pressure times that height, is higher than KIC, the fracture will continue to propagate in height. So it is the height of the fracture at very early on before it propagates into the upper and lower zone. If the fracture is so small here, then you're talking about the pressure times that height. Okay. Did I answer your question? So
I think you did, Dr. Solomon.
yeah.
Yeah, this concludes our Q&A session. There's another question about about the square root of time and G function, but we'll save that for next webinar.
Yeah, we'll cover the analysis next time. I may expand it. Testing, it can take a lot of time. We'll cover some of it and then we'll see.
Yeah. So yeah, thank you, Dr. Solomon, for dedicating some of time of your surely busy schedule to give this webinar. We are all grateful. Thank you, attendees, for tuning in from all over the world. Stay safe, wear a mask, and have a great day.
Thank you very much.